So, guys, today we'll talk about a very common data set that we use whenever we go into deep learning, and particularly whenever we go in computer vision problems. And this data set is known as MNIST data set. Actually, it is a data set which contains the handwritten digits of various people, and we try to train a convolution neural network on it and try to find out the accuracy, or try to find out the model which can recognize the new digits that we write. So in this video series, this series will be a two-video series. The first episode, that's this video, it will contain the video related the dense architecture of the this problem. So basically, we will be going for two problems, two approaches. The first is the dense approach, and the second is the convolution approach. So first in this video, we'll go for dense approach. Okay. Now the thing about this MNIST dataset is this: it contains images, and that images are 28 by 28 pixels, means they are 28 in height and 28 in width, and they are grayscale images. So there are no color channels; they are just grayscale images. That is, the color channel is one. So let's go and see how can we solve this problem using the uh, dense neural networks. Okay, so the first thing that we are going to do is we are going to import all the layers from the TensorFlow keras, and we will use those layers to create our model. And then the second step that we are going to do is we're going to load the MNIST dataset from keras datasets. So the MNIST dataset is available in various CDNs, like TensorFlow datasets has its own MNIST dataset, keras datasets has MNIST dataset, and I think the Google Colab itself has a sample data which contains MNIST dataset of 28 by 28 pixels. So we are going to use the keras because it seems simple using keras library to import that data set into our library and work with that data set. So let's go ahead and import first of all the libraries. Okay, so let's do that. So what I have done is I have imported basically the libraries and the layers that I'm going to use. So I'm going to use TensorFlow. I'm going to use keras, that's TensorFlow submodule. I'm going to use the dense and flattened layers for our classification problem of MNIST dataset, and I'm going to use the models module from this TensorFlow.keras. So these are the libraries, these are the models, these are the modules, these are the layers that I'm going to use in my dataset. So let's run this cell and see if this runs very perfectly or we get an error. So let's do this. So it gave an error. So the error is from TensorFlow errors. So basically, we had to write the sequential model, get us the sequential model, and I made a mistake. I wrote the models. So I'm telling you get the sequential model from models module. Now the thing about this keras datasets is that we need to load this, and there is a simple import statement and simple function to load the keras data set. So what we can do is we can say data is equal to keras. Now what I have done is I have initialized a variable in which I'm bringing the MNIST dataset from the keras library. Okay, so I'm initializing a variable, and then after initializing the variable, I am saying get me the training image, training labels, testing image, and testing labels from the data that I just loaded, and then do one thing, that data, that this training and testing splits we get, we have to use the load data function. That means we are loading from the data variable that we just created, and we are getting the data back into test image, train image, and test labels and train labels. So let's do one thing. Let's first see the shape of the train image. So if we can see, if we do print test, we can see that there are 10,000 images in the testing set that are 28 by 28 pixels. And if we in the same way we do for train images, then there are 60,000 images in this training set. That means we have a 60,000 image training data set and 10,000 test image data set. Now, let's do one more thing. Okay. Let's do one more thing. Let's try to visualize few of the examples from the training set. Okay, so we can simply say use matplot library for doing that, and the function that we have to use is known as im.im_show, means im image show, and we need to give it the numpy array. So first of all, let's import the library and let's write that code which is used to show a sample, or which is used to show an image whose pixels are stored in a numpy. Because if we can see the numpy, the training images are numpy arrays. Okay, so we do not need to see it because it is obvious that everything is numpy. So that's that. So what I have done is I have imported the matplot, and then I am telling it that you show me this the training image that is at the 0th index, and this is showing it in a third representation. So for black and white, we have to say that set the CMAP equal to binary. So we can say now that we have set the CMAP in a binary, now we can see this image in a black and white. But as humans, to us, this image is loosely visible to us that we can predict it. I don't know what it is. I think it's 5, most probably. Then it's very intuitive if our model does this prediction with an accuracy of 97, 98, or 95 above. So that means this shows that the power of deep neural networks, because we humans have such a long history of living in this world, and yet we are unable to. Maybe there are different images in this data set we won't be able to recognize because they are such tiny images, and our model is trying to predict, learn the features from those images, and get to predict the images that we are going to then input it. Okay. Now let's try to print the first image of a training set. Okay. So if we see print, if we will print, then we can see that there are the images. These are the numpy values. These are the pixel values of the images that are stored in them. You can see that there are 28 zeros in the first row. That is 28 zeros, and then there are 28 columns. So it's 28 by 28 pixel image. Now let us try to normalize the images, because in deep learning, whenever we are working with the images, we need to normalize the images. We need to normalize the image. What does that mean? We need to bring the pixels, because the range of the pixels is from 0 to 255. So we will try to bring the pixel values between 0 and 1. So how do we do that? It's simple. We just divide every pixel in an image with 255. And in NumPy, whenever we are dealing with NumPy arrays, it's very easy. We just say divide this by 255. Now, in this um, deep learning, these architectures, we do normalize the images. So we will write a function which takes the test image and training image as input and then returns the normalized image. So let's do that. So what I've done is I've written a function normalize image that takes input the uh, test image and the train image, and it just divides every pixel by 255 and returns those images back to the back to the function, or returns those variables back. Now all we need to do is create two variables that will contain that normalized test image and normalized training image. So we will say n train image for normalized training images and n test image for normalized test images. And we will call this function that we just created, that is normalize image, and we will pass the train image, and we will pass then the test image. Okay. So if we will run this function, we will get the normalized train image and normalized test image. Now, if we try to visualize, if we try to print the first array, the first image, the training set, we will see that the values are now between 0 and 1. As here, you can see that the values are between 0 to 255, some values are 253 and all that stuff. And you can see where the values are more, because here, if we will see the pattern of these higher values, we can visualize that they also make the shape of 5, right? So let's try to now see or visualize, not just visualize, let's try to print the values of the first image that's in the training, normalized training image. So we'll say print printed all the images. Yeah, it print all the images. As you can see now, the values are almost zero. So we will print the first image. Okay, we'll print the first image of this set, of this training set, and you can see now the values are between 0 and 2. Sorry, 0 and 1, not between 0 and 255. Okay, now we have normalized the image. Now we are ready for the network we build, and then we will pass the data, the normalized data, to our network and see what will be our accuracy. Okay, so now let's create a model, create a function rather than a model, and generate a model using that function, and then we will compile that model and then train the model using the data that we just. Okay, so let's go and write that function. Now, what I've done is I've written a function model. Okay, so it is creating a model, sequential model, and then it's returning the model, but it's printing the model.summary. What does it do? It gives us the overall summary of the model. What does it take as the input? What does it give as an output? And what activation function is used? How many parameters the model is going to train upon? And you can see the first layer I used is a flattened layer. What does flattened layer do? Because since we have the 28 by 28 data, but the dense layer, it works on a single vector. Okay, it works on a vector rather than a matrix. So our data is a matrix, so we have to convert it into a vector. So what does it do? It flattens. It takes the columns, it takes the rows, and stacks them together. Okay, it stacks them one after the other and flattens the image. It flattens the image, and then what we are doing is we are creating three layers. That is dense layer, the first layer, and second layer with 64 neurons, and then the dense output layer, which contains the neurons equal to the number of output units. It's equal to the number of the output conditions, output probabilities we have to get. And whenever we have a multi-class classification, what do? We use softmax as an activation function. And in rest of the cases, we use ReLU activation function. So I had a mistake in the spelling of the ReLU in the second layer, and I just rectified it. Now let's create a model and see the model summary of our data. So for that, we have to give it the input shape. First, let's get a variable input shape, which will contain the input shape that's 28 by 28, but that shape we will get from the training data. And then output numbers we will get from the labels of the training set. Okay, so let's do that. So first of all, we'll create an input variable. So what I just did is I hard-coded the output number of outputs we require. Now let's get our model. So we will say dense model. So we will say dense model is equal to model, and we will pass it the two variables, two arguments that we need to pass it. And then we will say outputs. And we will get our model back. So this is the model that we just created. It is so simple model. It just creates three layers of dense. And you can see the number of parameters that we are training upon is just 1,09,000 parameters. It is such a small network, but it will work tremendously, very impressively on our data, on this model, on this data. A few years back, this data was so important that it was very difficult to create a model for this kind of task. But now, even we, the beginners, are creating such models that will perform, that can give us the accuracy of almost 98, 97% accuracy. So this is how powerful the deep learning has become, how powerful the machine learning has become, and it will go on becoming the powerful. Okay, so it needs the engineers, it needs the students like us, like we. So in order to make it progress. Okay, so now we have our model. So let's do one thing. We will just compile the model using the optimizer and the loss function. Okay, so let's do that. We say that model dot. Okay, so we're telling it that compile. We're telling the model to use when he's going to train, when it's going to train, use the optimizer as Adam. Optimizer as Adam, and use the loss function as sparse categorical loss entropy, and then use the matrix as the accuracy. So after we run this function, and we can now train our model using the fit function. So what we can do, we can say dense model dot fit, and we will try to say 10 epochs. We will try for 10 epochs, and we'll see how much accuracy can we get in those 10 epochs. So we'll say train image. Rather than saying train image, we have to say n underscore train image, which are the normalized train image, and then we are going to say train labels, that are the labels that are associated with the training image, and we will say go for epochs 10. Okay, so we want it to go for 10 epochs, and let's see what we will get the accuracy after 10 epochs. So it's quite running very fast. See you after the training. So the training completed, and you can see that we have gone from loss of almost 0.06 to 0.015, and we have gone from the 97% accuracy to 99% accuracy. And this is the power of deep learning. We started right from the 97% accuracy and on to 99% accuracy. But this accuracy is on training data. So we will not judge our model right now. So now what we need to do, we will just evaluate the model on the test data that we have created when we split the data between training and testing data. So if we will say in the TensorFlow, how we do that, we evaluate the model. So how do we evaluate the model? We say the name of the model dot evaluate function and give this the input and the output variables. That is testing input and testing output. So how can we do that? We just need to run the evaluate function. Now, after running this evaluation function, we can see that we got a loss of 0.09 and we got an accuracy of 97%. Such powerful deep learning. Just a simple model with 3 layers and 128 neurons, 64 neurons in second layer, we got an accuracy of 97%. Means our model is 97% accurate. Can only if he will be given 100 images, he will just make mistake in 3 images, and 97 times he will be correct. And even if we round this off, it is 98%. So he will make mistakes in just 2 images. Oh, our eyes can make mistakes almost, I think, 80 times, because these are so much low resolution image that we cannot even decide what image is what. So this is the power of deep learning. Okay, so now what we need to do, it's just this completes our project. This completes our project's part where we use deep learning, where we use deep dense neural networks for the process, for the purpose of classification, or classifying these handwritten digits. Now we need to do one thing. We need to create a GUI interface inside the Google Colab library. Inside the Google Colab, we need to create a GUI library, GUI, so that we can write down that GUI and it will predict what it is. Okay, so for that purpose, we need to install Gradio. It's a library that gives us that opportunity to have GUIs inside the Google Colab, or to have the GUIs for demonstration purposes. So we will install the GUI and install the Gradio library, then import the Gradio and create the GUI interface. So let's go and do that. So how can we install the Gradio? We just simply say bang character pip install Gradio. This is how we install the packages in our notebook. Okay, so we say bang and usual pip command. Now that the module has installed, what we will do, we will import it, create user interface, and then set up our this sketchpad. There is an interface known as sketchpad into Gradio where we can write on that pad. So let's go and write that interface. Okay. So this is the way how we create an interface. We just say gr.interface means get us the interface from the gr library. But there is a function that we need to run, that on which this function on which this interface will call upon when we submit the data. So this function needs to be the prediction function. So let's create a prediction function. Let's slide the logic of prediction, and then let's return the predicted value from the prediction function as a text, because we said outputs equal to text. Okay, so we need to return that from the function and write that prediction function and pass that function to the function argument of the interface class. So we will define a function and then we will return the prediction from that function. So now I've written the function predict that takes input as an image. So this image is a 28 by 28 by default. From the sketchpad, it is 28 by 28. So I have to reshape it image. Or I have to reshape it in the vector form because our image is 28 by 28. So we need to take this matrix and create a row vector because our model was trained on the row vectors, on the vectors. So what we did, we just reshaped it to that vector. Now I'm saying that prediction is equal dense model dot predict classes. So predict classes is a function, is a method from the TensorFlow that lets us predict the classes, but it's going to be deprecated. So we can just say that get us the predict method, and then we can use the argmax function from NumPy to get us the that particular value that has the highest probability in the list. But right now we're going to say predict classes, and it's going to give us the class to which the highest prediction belongs that the model predicted, and we are going to return that prediction. Now let's try to run this function, run this cell, and see how our interface looks like and what does it give us. I forgot to write a method that is dot launch. It's very important for this interface to launch. So we will say launch. So I've said launch and debug equal to true. It means if I'm getting some error while uploading the image, while submitting the data, that error will be logged and will be shown to us. If we did not say this, we will not get an error. The cell will stop running, and by saying the debug equal to true, we will get an error and the cell will continuously run until we try to find and until we try to solve what the error is. So our interface is loading, and you can see that here is the running on the external link this. So if I go to this link, I will get to the external page, web page, where I can do the same that I can do inside this Google Colab notebook, and that's giving using this interface. Now the thing is that this link remains 24 hours open. So even if this cell stops, you can use this interface for 24 hours. And if you want to show, if you want to showcase your project's performance, you can do this by sharing that link. Okay, so now let's try to write on this pad something and see what our model predicts. I have written 5, so it's giving me an error. That's what I was telling you. It's because of debug equal to true. So now let's try to debug this error and see where we are getting an error. So the error was I had misspelled the reshape word for NumPy. So it was telling me that there is no reshape in the NumPy. So now let's try to submit this once again. So again, I have written 5, and let's submit it and see what I can see. I got 5 as an output. Okay, so there are other ways where we can output the result. We can output the highest probabilities, highest top 3 classes that it was sure about. We can predict it like that, but it's very difficult right now. It is somewhat difficult right now. So because we are on the simple dense model, we will see the text way. And when we are going to use the convolution networks, we will see that particular way in which we can predict the top 3 classes or 4 classes or 2 classes that the model was sure about. So now let's give some more examples and see how the model will work. So it's 4, it predicted 7, 8, it predicted 6, 2, it predicted 2. Let's try to write 3 as clean as possible. So it predicted 3. Let's try to write 9. It predicted 3, 4, 9. So we can see that because maybe we do not know how to write on the sketchpad using mouse. That's why we are getting so much of errors. But you can see that the model is working perfectly fine. And if we go to that link that I was telling you about, the Gradio link, then here we can access the same model, but it's outside our notebook library. So we can share this link and we can showcase our projectors for 24 hours if we want to do so. So let's try to write here again. Say we will write 2. Good 2. So it got 6 because it looks like a 6. It wrote 5. Let's see for 5. It predicted 5 very well. Let's go for 1. I don't know what it's going to predict for 1. predicted 5. So our model is making some mistakes because it's not that much perfect, but it's doing quite well. If we know how to write using mouse, we will see a far better improvement in their predictions. So this was all in this project using dense neural networks solving the MNIST dataset. And in the next video, we will see how we can use the convolution neural networks, which will do the same function but in an efficient way. If we got an accuracy of 97%, 99% in 10 epochs in convolutions networks, we will get that same accuracy in just 2, 3 epochs. So let's try to stay happy by using that we did this thing project using dense neural networks. This problem was unsolved some days back, some years back, because it was very difficult to predict and to make neural networks that could perform such tasks. But now we have that power. Okay, so now in the next video we will see how to use convolution neural networks to do the same task and get a better prediction and hopefully get better results than the dense neural networks. And we will see that the number of parameters that will be trained in convolutions will be far less than the dense networks. So that was all in this video. I hope you liked this project, you understood how to solve this project, and you were able to do this project by yourself by following along. And I bid you goodbye and stay safe, stay healthy. Goodbye. And also, I forgot to mention, if you like this video, please do share, subscribe. Please do share, subscribe, and like this video, and do comment below what you liked and what you did not like about the video, and what I need to improve in my presentation, in my speaking,